Hi all, it's our pleasure to make a presentation today. Me, myself, Carl, and my other teammates, Sihan and Sammy will present the topic, homomorphic encryption. Hope you all will enjoy it. These are the contents that we cover in the following slides.
Before we introduce homomorphic encryption, also we called HE below, we would like to tell a story. Alice has gold. She wants to make rings. She assigns a worker to use the gold to make rings for her. Gold is expensive. She is worried about the worker might steal the gold during the process. The question is, how should she prevent the risk? In order to solve this problem, Alice used a transparent box with a glove. Alice located the gold in the box using a key that only she had. As shown in the figure, a worker can wear this glove and work inside the box. Because the box was locked, the worker does not get the gold during the process. After processing, Alice could open the box using the key and get the ring. In a word, the worker was able to process the gold without having truly access to them. This is the correspondence of the story. The gold represents the initial data we do not want anyone else to have access to. The lock is the user key. The action to place and lock the gold is the HE. The processing is the application and the unlock is the decryption. And the ring represents the desired function of the initial data. So what's the meaning of the HE? It is the ability to process encrypted data that can be processed by others without revealing any of the initial content. The result of the computations will be remained encrypted and can only be decrypted by the private key of the owner. Calculations can be carried out on encrypted forms of the data is the essential.
This is the timeline of HE evolution. The concept of HE was proposed by Ronald and his other research team member in 1978. After that, within 21 years, two versions of the additive HE system were invented. In 2005, a new version of HE, which is multiplicative, was introduced by Dan and his team member. In 2009, a fully HE scheme was proposed by Dr. Gentry. Next, the basic function of homomorphic encryptions are key generation, encryption, evaluation, and decryption. Key generation is about the production of public key and secret key. Then encryption is related to the encryption of data and sending it to the targeted server. Evaluation is about the server processing the request and performing the operation requested by the client. The last step, decryption, is about the client decrypting the data using the secret key. Now we will talk about the properties of HE. So the first property is additive. For example, Pallier, given encryption of PT1 and PT2, we are able to compute an encryption of PT1 plus PT2 without having access to the secret key. The second property is multiplicative. For example, the RSA scheme, we can see that given encryption of PT1 and PT2, we can get a ciphertext encrypting PT1 times PT2 without accessing the secret key. There are three main types of HE. They are partially, somewhat, and fully HE. PHE only allows selected mathematical functions to be applied to encrypted data. SHE allows a certain amount of mathematical operation to be performed a limited number of times, while FHE allows any kind of mathematical operation to be performed an unlimited numbers of times.
In the following, we will talk about the applications of HE. Firstly, HE can be used for cloud computing. However, it is not realistic to fully trust the cloud provider. Therefore, we need HE, which can provide the mechanism that allows the cloud provider to perform the operations on encrypted data without decrypting them. This picture reveals the process in a more interesting way. Firstly, the client company sends the encrypted data such as encryption A, encryption B, and encryption C to the provider and sends a request to ask the cloud provider to calculate FAB for the client. The cloud provider stores the encrypted data for the client and calculates FAB with only the ciphers of A and B without knowing their plain texts. Then the result will be sent back to the client who has the key to decrypt. HE is an important stone in cloud computing security. HE can also be applied to data analytics in industries. Example includes protecting consumer privacy in tailored advertising, using financial privacy for stock price prediction algorithms, and doing predictive analysis of medical data. HE can also increase the security and transparency of democratic elections. For instance, the addition-based Pioneer encryption technique would be most suited for voting-related applications since it enables users to add up different values in an objective manner while maintaining the privacy of their own values. This technique could not only protect data from alteration, but also enable authorized third parties to independently verify it.
Now we would like to talk about the benefits and challenges of HE. There are many benefits of HE. Firstly, it allows cloud to be used securely and efficiently. With the help of HE, businesses can use cloud computing and storage services securely. This reduces the security risks on data and increases its usability. Also, businesses can perform particular computation on the data without considering the security applied on the private data by the cloud services. Next, it helps to establish cooperation between parties. HE allows a company to share its private and sensitive data with other organizations by hiding their true values. This is greatly helpful in encouraging creativity, innovation, and collaboration between parties regardless of reviewing sensitive information. Lastly, it is able to ensure regulatory compliance and privacy. HE allows businesses to operate in heavily regulated sectors such as banks, healthcare, and government. Most data can be transmitted and outsourced for research and analytical purposes without restriction due to the risks of non-compliance. The main idea of applying different HE is to ensure that confidentiality and privacy of sensitive data can be protected. Unfortunately, there are many challenging issues which can affect the performance of HE. The first one is effectiveness and efficiency. There are few HE schemes that are stated as effective and safe to be used in real life applications such as partially HE. However, due to its own design and properties, these schemes have a great limitation on performing more than one kind of operation, such as addition or multiplication at any single time. This is not ideal for real-life situations where most applications are required to handle complex computations that contain numerous operations. One solution is to have different schemes work together to fulfill the targeted requirements of a particular application. Other than that, HE is slow and not efficient, and this becomes a significant barrier for this encryption method to be adopted worldwide. Nonetheless, someone has to put effort into making things change. Companies such as Microsoft and IBM and researchers such as Dr. Gentry are intended to improve the speed of HE by reducing the computational overhead. Besides that, robustness is another challenge of this encryption. The size of the encryption key is the key factor that affects the robustness of HE. The longer, the better. For instance, the public key of RSA scheme is suggested to be greater than 1024 bits in order to ensure a certain level of safety and security. However, everything comes with price. The increment in key size in turn greatly leads to delay in system processes. Lastly, we should consider the security issues of this encryption. The inventions of HE allows the delegation of computation to other parties to be possible. However, some loopholes found in this encryption related to outsourced calculation can be problematic. In fact, this encryption has a malleable design and this makes this not a compliance to the indistinguishability ciphertext under adaptive chosen ciphertext attack. Also, in some cases, they are vulnerable to malware. Consider the case of secure voting system that use adaptively HE. If one of the voting booth were to be infected by malware, there is a great chance that the malware could manipulate votes before they are submitted. The same threats could happen at any other system that exhibit homomorphism. In this presentation, we have briefly presented the different homomorphic encryption system, such as partially, somewhat, and fully HE. We have also introduced some of their application benefits and potential challenges. We are looking forward that there are more improvements and researches can be done on this encryption in order to provide more option of security and quality services in real life application. Lastly, thank you for having you all with us today.